I'd like to show some simulation, Radia and Mathematica on Windows. First of all, I'd like to some schematic structure of multiple wiggler we want to simulate. Simulation. So the multiple wiggler has 9 poles. Each pole has permanent magnet before and after. Produce the magnetic flux higher at the pole position. We have 9 poles in this position with 2 ending poles. We have an upper and lower magnetic plate produce higher magnetic field between this gap. The gap can be changed by motor to produce just the magnetic field in between. We may show smaller pole. We use the 5 pole to reduce the length of total multiple wiggler. The gap will be changed to 15 instead of 20 for this. This is the schematic drawing magnetic array. In this case, 9 poles or 2.5 period. 5 poles or 1 period plus 1 pole. Then we have a specified magnetisation of the magnet against the pole. This is the magnetic field as a function of the gap. When the gap reduces, magnetic field is available flux from the smaller gap, higher flux, higher X-ray energy. The pole sandwich with the permanent magnet not only transverse but longitudinal. The green magnet is called side magnet. The red magnet is called main magnet. Each magnet specifies this table, tension, and chamfer. The permanent magnet is vanadium iron bond. The pole is vanadium permanent iron copper alloy. Based on this size of the magnet and pole, we make a model in Mathematica and make a simulation of the idea available from ESRA website, Mathematica version here. We can also use the Python version, which will be present in different videos. Now concentrate on Mathematica idea video. So the number of pole, even pole, and odd pole for symmetric and asymmetric configuration. Now we use the odd pole asymmetric configuration. Actually, we can do both, even or odd pole, depending on the number of. So even pole or odd pole, different model we have to create. So we have to have target number of the pole. The number of pole increase, the flux increase. But the number of pole increase, the total length of depend on the operating storage condition. Have to design the total length, number of pole, available gap. The gap can be reduced in vacuum condition, but in this case, we are not going into detail about. We can also optimize the width, length, height of the magnet and pole to optimize the magnetic field. If magnetic field higher, or the width of pole increase to make the electron beam operation much easier for injection the top-up mode. Now we go to the website. My code is available from the GitHub. And in case of Mathematica, you can download this file. Now we can start. Yeah? Now we open Mathematica file from the GitHub. The Radia already installed as an add-on. So this is the example file from the Radia, already modified for multiple figure. But some of the description is not updated. Original file is for undulator. Adjust the file to regular. Now we run the Radia. Define the magnetic material, have a data magnetization, and can put here. But if you have a neodymium boron magnet, the Radia has a setting. If the company provides a specific magnetic field, you can put. Now you can choose model of the odd number of pole or even number. Now we go to run code. To create a geometry, have a function here, number of pole. Specify the parameter. For example, the gap of analytic array, number of periods. Number of periods 2 means 5 pole configuration. The period, one period length, 220 millimeters. Size of the pole specified here. Number of subdivision. So this is a unit element method. You can specify a large number of elements. You can more accurately calculate the magnetic field. However, the calculation time is long, so simply use one word. For example, color of the pole, geometry presentation. Terms are also specified. The magnet also specified side magnet in the pole side magnet. If you have a gap between the pole magnet structure, you specify here. Material of pole, material of the permanent magnet specified here with the magnetization. If we run this, we can plot the geometry. Okay. Check the correct geometry on. So simply say 1, 2, 3, 4, 5 pole with gap between this is 50 meter. Total length specified here 40 millimeters. We want to see only the pole structure, specified pole, only the quasi magnet, magnet, magnet structure, I will specify and configuration correctly the whole structure. Now we go to the model. You get a magnetic field 2.76 Tesla. In the case of even pole, the peak magnetic field position. Plot magnetic field. So the 5 pole with 2 ending pole. Magnetic field can be plotted I direction, X direction. This uniform magnetic field is important with the top-up mode. It's not a uniform area. Is very difficult to make the top-up mode operation. In trajectory, electron beam, trajectory 1.2 gigaelectron volt. Translation of the electron beam trajectory is not correctly optimized. Of the electron trajectory also not in the gap or ending magnet structure to make orbit deviation to minimize. To minimize that kind of orbit deviation, we normally check the field integrals. This is the first field integral. So this part should be very close to zero for operating gap or operating energy. Very small. So this magnetic structure probably for president is feels enough during injection you have been top up. The magnetization vector also can be displayed. You can see that the magnetic field magnetization action up and down. I also up and down correctly. You see the permanent magnet with specific small arrows. Magnetic force also important. Next to mechanical structure of the multipole wiggler. So in this case, 45 kilonewton will be the magnetic force at the force. The magnetic force increase will still increase when the gap This is checking material when part was specified by this. We also optimize the parameter, the function specified for output. We can scan the parameter, for example, the pole y direction size can be varied from 10 to 120 millimeter with step 5 millimeter. So, and play big magnetic field. This part will save the text data to this file name, and this part will plot. So this is the pole length and the field. So the pole down 30 millimeter make maximum field. This one is 1 for the x direction. For width, 10, 10, 25 millimeter. But as done, we scan already pole length to be 120. We have reset very come to and function again into the parameter x of this segment 0 same time. Try this. For width highest around 30 millimeter to 40 millimeter. However, this pole width probably shorter than original design because of the injection issue mentioned. The original design is at 70. So of course, the peak magnetic field is used to inject the beam gap is small. It's really critical to have a uniform magnetic field rather than the peak magnetic design 70. Of course, you can change the permanent magnet direction or chamfer or number of subdivisions to optimize the condition. This is also can be set to integral upon the gap distance to any magnet finding magnet height. The magnetic force also as a function of the gap and finally can get help. However, magnetic force upon the Take time watching this video.